Good morning. I am Noorullah Khan, the coordinator for my team's COMP3210 Big Data Assignment 2. My teammates are Ali Sheikh and Hamzah ALJUBOORI. So I'll start with the introduction. Task 1 was done by Hamzah ALJUBOORI and Task 2 was done by Ali Sheikh and Task 3, the report, was done by me, Noorullah Khan. The purpose of this assignment was to apply advanced data structures and algorithms for efficiently solving complex data problems in data retrieval and analysis, to demonstrate the implementation and effectiveness of spatial data algorithms, including nearest neighbor search and skyline searches using arteries. So I'll start by giving a brief overview of task 1. Task 1 was the nearest neighbor search done by Hamza, and it used the parking dataset and the sequential scan-based method and the best first algorithm, and used divide and conquer with the BF algorithm. So a really simple step-by-step is shown here on the right, how it goes through initialization, sequential scan, branch and bound, then divide and conquer. More in detail is available in this diagram, where lowest starts the set in query and it's read, then it's created an artery, and then the artery inserts points into the artery and chooses the subtree, and then it can either add the data point or it can handle overflow, which will then spill the node and so on. And once it's inserted into the artery, it can then perform nearest neighbor search, which will start by saying if this a leaf node, and then calculating distance and and then or choosing a subtree, then recursive search. And after that, it's going to do the sequential scan, the branch and bound, and the divide and conquer, and the results are going to be saved in a file. Now a brief overview of task 2, which Ali did, and it was the skyline search. So it was a branch and bound skyline search and BBS with divide and conquer. So a flow chart's available here, how it says sequential scan, uh, the branch, the branch and bound, and then the divide and conquer, and it goes through data loading the data set, queries, and so on. Then it goes through the sequential scan, creating the artery, splitting the data set, and so on. And the results are written to a file. More detail is over here, how it starts on the right here with the main function, reading the data, opening the file, reading the lines in the file, then generating objects, and with that, it then goes to perform a sequential scan, which includes the steps of initializing skyline point, start timer, iterating over dataset, checking if it's dominated, then adding to skyline points if not dominated, calculating execution time, and returning skyline points and time. After that, it goes to the branch and bound skyline. So this performs a BBS algorithm, initializes the R tree, and inserts homes into arteries and so on. After that, it goes to the BBS with divide and conquer. It does that whole step and then it writes the results to the file. Next, going to a bit of theory about the overview of arteries. So arteries are spatial data structures used for indexing multi-dimensional information, typically suited for geographic data. Its primary utility is to facilitate rapid queries, and it's especially efficient for range searching, nearest neighbor searching, and overlap searching, especially in very large data sets. And the art tree is a balanced tree, and it uses bounding rectangles called the minimum bounding rectangles MBRs to encapsulate objects. The key features of an tree are the hierarchical structure, which means that the tree is high balance with leaf and internal nodes, and leaf nodes contain entries that represent data object, and each entry is a bounding rectangle enclosing a data object. Internal nodes store entities that are bounding rectangles, each enclosing all rectangles in the child nodes. And balance trees, so all leaf nodes at the same level, which means the path length from any root to any leaf are equal, and this is critical for performance consistency again across all queries. And dynamic insertion and deletions, so our trees handle dynamic data set changes effectively, allowing entries to be handled and removed without requiring a complete restructuring. So next, we're going to the construction process of the R tree. So Inserting into an artery, you choose a leaf, so you navigate from the root to the appropriate leaf node, and it should contain the new entry based on minimal area enlargement and the bounding rectangles. And insert and split, so you insert a new entry into the selected leaf node, and if the leaf node overflows, meaning it exceeds the maximum number of entries, then it needs to be split. Splitting propagates upwards as necessary, possibly adding new levels to the tree. So the process explanation is that load data points are loaded directly into the code. Index creation is that our tree index is created by iterating through each data point, and each point is inserted into the tree with a bounding box defined by the point's coordinates, since points are zero-dimensional in terms of area, and spatial indexing, and this method is used which automatically handles the placement of the new point into the correct node of the artery, including choosing the correct leaf based on minimum bounding rectangle enlargement and performing splits as necessary. So now I'll hand it over to Hamza so he can speak about more in detail about his task 1.
Good afternoon. My name is Hamza, and today I will be presenting how I solved the nearest point using 3 different algorithms, which is the sequential scan, branch and bound, and divide and conquer together with branch and bound. Um, so the tasks basically involves finding the nearest facility for like 200 user queries based on the 3 data sets, which are restaurant, shop, and parking. So each dataset contains a 2D point with a geographical coordinates, and there is 200 user queries as well. Each represents a 2D point with the same format as the dataset. As you can see in the example here below, there's a format for the dataset, the query, and an example for both of them. And for the first algorithm, which is sequential scan, I had to calculate the distance between each query point using um, Euclidean distance, where I used the NumPy um, library to calculate it. There's a code snippet here on the next page. I'm gonna explain some of the code for each algorithm. So for like the sequential scan, basically it iterates over each query point, and then it calculates the Euclidean distance, as you can see, using the NP Linelk norm, and then it identifies the index of the point with the smallest distance, and then it just retrieves the coordinates at the end, and appends it to the list. For the branch and bound, we had to construct an artery. That's what was said in the assignment. But then I found out that we had to use the code which was available for us on iLearn. At first, I just used an artery library, so I had to do that again and use the code from iLearn to construct the artery. Um, and then basically just use the BNB algorithm with the artery to find the nearest neighbor. And for the construction of the artery, I had to use the data points and the minimum bounding rectangles. So this is just a snippet as well of the artery code. Basically here I'm just initializing the artery itself, and then the artery just iterates over each point in the dataset. And for each point um, it inserts the point into artery using just the insert method basically. While for the divide and conquer, Of course, it's divide and conquer, so you have to divide it into two subspaces and then construct the R tree for each subspace. After that, I applied the BMB algorithm and just compared the result of each subspace to determine the nearest neighbor. The code snippet here, which was a bit bigger than the others. You can find, of course, the full code in the submission, but for this part here, basically, I'm calculating the median of the x coordinate in the data set and then just dividing it into two subspaces, left and right. After that, the R creates the R tree for each subspace and it iterates over the query points. For each query point, it performs the nearest neighbor search in both left and right tree, and then it compares the distance from both subspaces and selects the closer point. And after that, it just appends it to the result, including, of course, the ID, the coordinates of the nearest point, and the distance. So each algorithm had its own, draws and advantages. But if I had to compare them, like I would say the sequential scan is accurate in ensuring the algorithm is complete and identifies the nearest point. Typically, it's the longest as it involves calculating the distance from the query to every single point in the dataset. And the average time per query, I would say, is high since it processes each query point with a linear search through the entire dataset. And that's just not very practical if the dataset is really big. So I would say it has like a time complexity of n multiplied by m, where n is the number of data points and m is the number of queries. So yeah, the time complexity could get, it's not really the best. While for the branch and bound, it's generally accurate due to the R tree structure, and it's significantly less than the sequential scan because of the R tree, as it reduces the number of calculation, so it has like a lower average time per query than the sequential scan. I would say the time complexity is log of n multiplied by m, where n is the number of datasets again and m is the number of queries. And finally, for the divide and conquer, it has a high accuracy, but it's slightly based on how the dataset is divided. So it has a typically less running time than both the sequential scan and branch and bound, as we are dividing the dataset into two subspaces, of course, which reduces the search. And it has also the lowest average time per query as it combines the R tree with the divide and conquer approach. So the time complexity is around log n also multiplied by m, similar to the branch and bound. But this method is very efficient with very large datasets. That's why it's a bit better, in my opinion, than the branch and bound by itself. So, like in conclusion, I would say the best performing algorithm is the divide and conquer with the branch and bound, as it offers the best balance of accuracy, efficiency, and also leveraging the R tree by dividing it into two datasets. So this way it minimizes the search space and the processing time. And the branch and bound is not so bad. It provides a significant improvement over the sequential scan by using the R tree. Like it's very highly accurate and scalable. And I think, in my opinion, the worst one was the sequential scan. Like, while it guarantees accuracy, it still has to go over a linear search, which is not very practical in very big data sets, so it results in longer running time. So yeah, in my opinion, I think the best one was the divide and conquer together using the branch and bound with the R tree and everything. And yeah, that's all about it for task one. Ali will go over everything in task two, but that's all over for my part. Thank you for listening and have a good day.
Hello, everybody. Good morning. My name is Ali Hasan, and I'm here to present task two of our project. Task one was presented by Hamzah, and task three would be presented by Noorullah. So, my task is basically based on skyline search. So, this presentation would cover the application of R-tree-based algorithms to identify all the optimal homes in terms of the cost and size. The problem in this task is that we are given a data set which comprise of information about houses in terms of the cost and size, and we would be discussing about its problem and the algorithms which we use, and the results which we would be obtaining through performing all the algorithms to find out the optimal homes. So coming towards the problem statement of this this task is basically uh, a task related to real estate, which includes information about different houses and their cost and their sizes. So in real estate, for instance, we have to find out homes that balance the cost and size, because this information is very important for buyers before making the final decision about which house to buy. So as buyers often want the best value for their money, so which means finding homes that are neither too expensive nor too small would be the most beneficial for them. Hence, a skyline search algorithm helps to solve this problem by identifying homes that are optimal in terms of both cost and size. So essentially, filtering out homes that are dominated by others, meaning there are no other homes that are both cheaper or larger. We In this task, we are given three data sets where we have selected one data set to perform our algorithms to find out the houses in terms of their optimal size and cost. So coming towards the code, this is the code which which we have used to read the data set, and we have used the function to list out uh, the homes and the information presented in the data set. Now coming towards the first algorithm which we used for our problem is the sequential scan-based method. So this sequential scan-based method is basically the simplest approach to skyline search. Uh, this involves checking each home in the data set to see if any of it's dominated by any other home. So this means that comparing each home against all others to determine if there is another home that is both cheaper and larger. Uh, this method is but if we by using this method, uh, we got to know that this method can be very slow for large data sets, because it requires comparing each home with every other home, leading to more complications while performing this method. So this inefficiency is, we can say this is a drawback, especially when the size of the data set grows. So looking at this slide, this is the this is the function which we used to perform our sequential scan-based skyline search. Uh, the algorithm in this code, the algorithm iterates through each home and checks if it's dominated by any other home in the data set. If a home is not dominated, it is added to the skyline set. This approach ensures that only the optimal homes are included in the final skyline, but this process can be very slow due to the large number of comparisons needed in this method. So coming towards the second algorithm, which is a branch and bound skyline. In order to improve the efficiency of this task, we would be using the branch and bound skyline algorithm. So this method would be utilizing an R tree and a spatial data structure that organizes data points hierarchically. So by constructing an R tree for a data set, we can quickly uh, go through all the search space and eliminate many non-skyline points early. So this would reduce the number of comparisons needed and speed up the search process. This algorithm is, we can say this algorithm is more complex than the sequential scan, but the best thing about this algorithm is that it provides significant performance improvements, especially when we would be using larger data sets, which we currently are. So moving towards the code which we use to perform this algorithm is, as we can see that the first step is constructing the R tree, where we have imported the library which organizes the homes based on their spatial properties, cost and size. So the branch and bound skyline algorithm then cuts through the R tree efficiently by pruning the non-skyline points and it identifies the optimal homes. This approach basically uh, reduces the computational load compared to the sequential scan-based method, which was more complex. However, in while using this approach uh, uh, is more efficient while when working with the larger data sets, because it was able to produce the output more quickly compared to uh, the sequential scan-based method. Now moving towards the third algorithm, which we used for our task, was the branch bound skyline with divide and conquer. So in divide and conquer approach, this further enhances our efficiency by dividing the dataset into smaller subspaces based on their cost and size. As it's a method which is using divide and conquer, so we would be dividing our dataset into smaller subspaces, and each subspace is then processed. Each subspace would then be processed separately using the branch and bound skyline algorithm. So the divide and conquer approach would reduce the complexity of the problem by breaking down into smaller and more manageable parts, which we can say. And in this approach, once the local lines are identified into each subspace, they are integrated to form the global skyline using a one-dimensional dominant screening method. This method is particularly effective for when working on with larger data sets. Moving on with the code which we used for this approach. Uh, for this approach, the data set is divided into subspaces based on their cost and size, as it's a divide and conquer method, and an R tree is constructed for each subspace. The branch and bound skyline algorithm is then applied to each subspace to identify local skylines. And then finally, the local skylines are merged to form the global skyline. So, summing up this approach, it leverages the divide and conquer strategy to handle large data sets more efficiently, which means that it's a more powerful approach compared to the sequential scan. And also, it can be said as a more useful and a more stronger approach than the branch and bound method as well, because in it, the data is simplified into more smaller tasks. So now we would come towards the implementation details, which we used in our task. So we in basically this task, we used the three algorithms, which were sequential scan based method, branch and bound skyline search method, and the branch and bound skyline with the divide and conquer approach. So the challenge which we faced in this in performing these tasks was handling large data sets efficiently. Constructing and traversing the R-tree required careful optimization to ensure a good performance. We used libraries which were the existing libraries in the model with their with all the relevant details of each code to help with the R-tree construction and skyline search. This provided efficient data structures and algorithms to support our implementation. So coming towards the results of our task and the algorithms which we designed in finding out the best homes. So we compared the efficiency and accuracy of each method, and this this slide basically presents the results which we obtained from each data set using the three algorithms. So we can say that the branch and bound skyline and the branch and bound skyline with the divide and conquer approach showed more significant improvements in terms of the execution time and the output which it produced compared to the sequential scan-based method. So these results demonstrate the scalability and performance benefits of using the R-tree based algorithms for skyline search. So this slide basically presents you the code which we have used to present to get our results into a text file. So this code is basically used to present present all the results which we obtained from the three algorithms to text files. Coming towards the conclusion and summing up the entire task, we can say that we successfully implemented and tested three skyline search algorithms on real estate data sets. Our findings basically indicate that R-tree based algorithms, specifically the branch and bound skyline and the branch and bound skyline with the divide and conquer approach, are highly effective for skyline search. These algorithms provide significant improvements and are well suited for applications in real estate decision making, where identifying optimal homes is crucial. So basically, using the skyline search is more important when working with larger data sets. For instance, this data set where we had to find out the best homes in terms of their best size and cost, and we were successful in performing all the three algorithms and getting all the results which we wanted. So this was all from my part. Thank you for listening, and have a good day. Bye-bye.